Hello, everyone, and welcome back after our summer break. This is the first Atto Fridays talk of the season. We are very happy to introduce Professor Wendell T. Hill III. He is a professor at the University of Maryland, College Park, with appointments at the Institute for Physical Science and Technology at the Department of Physics. He is a fellow of the Joint Quantum Institute and is also the director of Interdisciplinary Graduate Chemical Physics Program. He's a native Californian. He was born in Berkeley, grew up in Southern California, and he's educated at the University of California, Irvine, and also Stanford University. He left the Golden State, much at the behest of his bride, who earned her graduate degree at Columbia University, for a 2-year NRC postdoc at the National Institute for Standards and Technology, NIST, after which he was recruited and joined the faculty at the University of Maryland. And Professor Hill has held visiting positions at institutes in Asia, Europe, and South America, as well in the US. And his research interests and journal publications range from high-energy particle physics to the ultras in atomic, molecular, and optical physics, ultra-intense, ultra-fast, and ultra-cold, with emphasis on quantum dynamics. And he also authored an article in the Encyclopedia of Applied Spectroscopy, an AMO physics textbook, and an e-book on quantum vacuum, which is his primary scientific pursuit today. Finally, he has served on several scientific advisory committees, domestic and international, was the program officer of the AMO program at the National Science Foundation, and has been honored with an election to the American Academy of Arts and Science. And we're really looking forward to his talk. Today, he is going to talk about vacuum and is going to be about times which are even shorter than attoseconds. So thank you so much for accepting the invitation and for supporting us. The floor is yours. We're ready to start.
Okay, well, Carla, thank you so much for this invitation. I'm been looking forward to this. So I'm going to talk a little bit about what my primary interest is now, and that is using very short pulses and very high intensities. And I'll explain where we get sub-attoseconds as we go along. So this is a story that started essentially back at the beginning. As I had this quote from the Bible that says that in the beginning God said, "Let there be light," and there was light. And so I like to start often with this quote from J.J. Thomson, which says, "The study of light has resulted in achievements of insight, imagination, and ingenuity surpassed in any field of mental activity, unsurpassed in any field of mental activity. It illustrates, too, better than any other branch of physics, the vicissitudes," I like that word, "of theories." That's changeability. So probably the first application of this is to light itself. Now, light goes back to the beginning, as I mentioned, and it's been gone back from particles to waves to particles, and now both. And on record, these two gentlemen first started talking about light and vision and where that comes from, basically from stuff coming off whatever the element is that you plan to see. And then there's some image that's generated in your eye. So this sounds a little bit like this corpuscle business that Newton started. He sort of, well, he didn't start it because it started before him, but he sort of formulated this idea of that light was sort of a particle or this corpuscle. Now that went along for a while until Young came along about 100 years later and did his famous experiment with interference. And then, of course, the whole physics world said, okay, it's got to be a wave. Well, that lasted for a while. And then quantum mechanics came along. And then quantum mechanics, of course, you know probably pretty well these three of these gentlemen, Einstein, Planck, and Compton, and they were very instrumental in this idea of the photon. But the person you may know a little bit less is this guy, Lewis, who actually is given credit for coining the idea of photons. And now we have this duality of waves and photons, which you've all known since you started studying physics. So I'm going to talk a little bit about light and some of our ideas and what we can do, hopefully in the near future, because we're getting to a point where we're going to have tools that will allow us to do some studies that are the theory of which is nearly 100 years old now. So before the 60s, before the laser, and imagine there was actually life before the laser, light sources were quite weak, and you basically were only able to look at linear features. And then once the laser came along, now we could focus the light. It had a lot of different properties, which most of you already know. But one of the properties that of interest here is that we can focus it down to a very tight spot, and we can then have a lot of intensity. Now, here's a picture that sometimes goes by the name of the Moore's law for laser intensity. We've had several Nobel Prizes for lasers, and then at the beginning, of course, the lasers were relatively weak, and then as we go up this scale, you see that we had Q switching, mode lock, and then the thing that made a huge difference was this chirp pulse amplification. And since that time, the intensities or the power really has just been going up exponentially. And as you can see in this chart, there's some places that you probably are familiar with, and we're going to come back and talk about a few of those. But here what we have early in the last decade, well, probably late in the last decade, we had petawatt lasers. So that's 10 to the 15 watts. That's the power that was in the laser. Because it's a laser, because it's coherent, you could focus it down to a very tight spot, and you can get intensities that start to approach 10 to the 20, almost 10 to the 21 watts per square centimeter. We now have lasers that are about 10 times that power, 10 petawatt, and there's some on the books that will go even higher than that. You can see by the diagram that the spot size for the 1 petawatt laser was on the order of 10 centimeters. The spot size for Eli NP, which is one of the 10 petawatt lasers in operation at the moment, is almost half a meter. So the beam gets big, and you have to make it big so you don't destroy your optics when you start to move the beam around. But you still focus it down to a very tight spot, and you can get very high intensity, and that's what we're going to think about today. Let me get rid of, oops. Okay, so let me go back. Sorry, we had a hiccup here. We'll go back. All right, so with intense lasers, we now have a scale. We have different things that we can now work on with lasers. So here are some of the regimes. Now you're likely to be familiar with the lowest intensities, and these lowest intensities now can basically allow us to do low order processes, multi-photon absorption, 2-photon absorption, we can do saturated absorption, a lot of things of that kind at this low, what I call non-relativistic regime. The next regime you may be quite familiar with, since this is an attosecond type talk, and that is what I call the ionization regime. This is a regime in which if you put an atom in this beam, it's going to ionize. And it's the reason we have high harmonic generation and in attoseconds. The next regime I call the relativistic regime. And this is a regime where the laser intensity is so intense that you put an electron in it, and in one cycle, it becomes relativistic. And this little cartoon shows you what's going on. There's a parameter that I want you to recognize. It's called A naught, which basically is the scaled vector potential. And it's scaled by this MC. And when A naught is about 1, it corresponds to an intensity of about 10 to the 18 watts per square centimeter. Everything ionizes pretty much at that intensity. This goes by a name called the classical critical parameter because it's really ionizing it, primarily as a classical, following classical physics. And we'll get into that a little bit more. So, but you get strong field ionization. You get things like relativistic electron vacuum acceleration. As I mentioned, the electron becomes relativistic in a single optical cycle. The magnetic field becomes important, and now you can push the electron in the forward direction because V cross B has to be taken into account. So things are all relativistic now, and things are very different. You can get MEV and multiple MEV type of energies in this regime. Now the electron really has a lot of energy, and it can do some interesting things. Accelerators, for example, people are basing on this regime. For us, it's useful for metrology, and we'll talk about that, what that metrology actually means. But then there's another regime. This is called the vacuum response regime. At least that's what I call it. This A naught now starts to reach a value of about 1,000. And that's pretty important because now A naught for the proton, because the proton is almost 2,000 times more massive than the electron, it too can become relativistic in a single cycle, and things now start to look quite interesting. We can have relativistic acceleration, so in principle you should be able to make accelerators out of lasers for protons. We have very strong field quantum electrodynamics, and this is what I want to sort of discuss with you today. And in particular, this diagram here at the bottom, which goes by, it's a Feynman diagram, which goes by the name of a box diagram. And what you see are the wiggly lines are the photons. The straight lines are the fermions, which in this case are electrons and positrons. And it talks about how light itself can scatter. And it scatters through these positrons and electrons that are buried in the vacuum. And we'll see how that might come about. To see this, we need to have a pure vacuum because we have real electrons which scatter more readily than these other electrons that come out of the vacuum, and we'll see where those originate here in a second. Okay, so what happens here in this last regime is something called vacuum breakdown. And as this cartoon is showing you, when light just propagates in the vacuum, it's going to start creating electron-positron pairs. And so we can see how that works. And one of my colleagues likes to say you can never get intensity higher than this because it'll just break down into electron-positron pairs, and then that will be the end of the story. So what I'm going to talk about here for the rest of this time is outlined here. I tell you that the electrons and positrons are going to be coming out of the vacuum. So this is what is known as the quantum vacuum, and I'm going to tell you a little bit about what that quantum vacuum is. Talk about what we can learn. Again, some of the theories go back 100 years. We'll look at the state of affairs of what we can do with lasers today, and then turns out we're going to introduce another parameter called chi, and then we're going to look at experiments above and below this chi. And finally, I'll say a little bit about the technology that's needed to actually see some of these things, which is what we're based on now, because we need to develop the technology in order to go forward. Okay, what is the quantum vacuum? Well, let's start off with the classical vacuum. The classical vacuum basically is the absence of everything. So it's empty space. There's nothing there. No radiation, no matter, nothing. The quantum vacuum is slightly different. It's the lowest energy state of the vacuum. There are no real particles. There are no energy sources, but there's something called quantum fluctuations. And you're familiar with that. You know what the ground state fluctuation is in let's say, a diatomic molecule. It always has this half unit of energy there in the ground state. So there's these fluctuations, and that's going to become important as we move forward. Now, it turns out there's lots of different kinds of vacuum, and I'm going to talk about one in particular. So we can have the first vacuum that came out from quantum field theory here was what I call the QED vacuum, and that has to do with electrons and positrons and so forth and photons. This won a Nobel Prize for developing these things back in 1965 for people that you have seen before, these people. And this is what I'm going to call the QVAC, and that's the quantum vacuum. And it basically has to do with electrons, which are fermions, and of course they're antiparticle positrons, and then the gauge photons are the gauge bosons, which it mediates the interaction. Now you can do the same thing with QCD. Things are a little more complicated. They got quarks and they got gluons, and there are many more of those. At least in QED, we only have one gauge photon we have to worry about, and then of course it gets more complicated and we go to the weak interaction. But we're going to focus simply on the QED vacuum today. Now, it goes back to, again, the 1930s when quantum mechanics was developed, and Schrodinger, of course, came first. The Schrodinger equation, of course, is non-relativistic. You have to introduce things like spin artificially, but you can make it work. But there was a push to make this relativistic. And Dirac, there's several versions, but Dirac's version of a relativistic equation called the Dirac equation was quite helpful. And it solved the problem of the spin, for example. But the Dirac equation has 4 solutions, as many of you probably know. 2 of those we recognize. One is for the energy and one is for the spin. But then it had 2 others, which turned out to be negative. And the negative became a problem. Now, we're not so uncomfortable with negative solutions because that's what we do in gravity, and that's what we do with an atom. The negative solutions are the bound states. And of course, potentials, it just depends on what you want to call 0 as to why it becomes negative. But in this case, if we have these negative energy states, which like the positive energy states go up to infinity, these negative energies go to infinity down, and that creates a real problem because the electrons would fall down into these states. And Dirac's brilliant idea was to, well, let's fill them up. So they're all filled up so the electron can't go down because they're fermions. And so when you see an electron in its ground state, then it's twice its rest mass energy above these negative energy states. And so everything's cool. And so the vacuum now is going to be made up of these things. And it didn't take long for people to start to think about, well, if we have this gap, why don't we excite these particles? So if we have electrons down in the ground state, we can excite them and put them up in into the upper state. And there was a lot of discussion about that. But as I mentioned before, quantum mechanics has this idea of fluctuation. And so we can have electrons fluctuating in there. And that means we could have electrons that can fluctuate. They can go from the ground state up to from the negative energy states to the positive energy states. Now, the electrons in the negative energy states are virtual. We can't see them, we can't do anything with them. But the ones in the positive energy states now, they can actually you can actually excite them. And so when the electron from the negative energy state momentarily jumps up to the positive energy state, that leaves a hole in the negative energy state. Dirac interpreted that as the positron. So now we have an electron-positron pair, and what you see here on the screen is actually that electron-positron pair becoming visible in what we see. All right, so creating these pairs. How do we do that? So this also started a long time ago. Oppenheimer was part of this first thought of, well, let's take a gamma ray and let's just excite it. That was developed a little more fully by Bethe and Heitler. They recognized that you have to conserve energy and momentum, and so they put this next to a nucleus, and they started talking about how to do that. And then it was understood that you needed 2 photons. Okay, 2 photons could come together, and you could then create a pair of electron and positron. This is not so unusual because we see this all the time. If we have an electron and a positron come together, they will annihilate each other and give you 2 photons. This is a classical experiment that is done in advanced physics courses, for example. But this one, though, has never been seen. Going from photons to electron-positron pair has never been observed, sort of. And I'll tell you one caveat to that. And the reason it's so hard is because the cross-section is so incredibly small. The cross-section peaks at photons of the mass of the electron, so that's about 500 keV of energy, and then it falls precipitously after that. In fact, the cross-section scales as omega to the 6th power. So if you have a gamma ray, it's going to be incredibly higher cross-section than if you have a visible photon at 1.5 eV. And so that cross-section is very, very small. So you'd have to have an awful lot of photons. Unfortunately, we don't have a gamma laser yet in order to do some of these experiments, and so that creates a problem. If you go into X-rays, for example, and there are some experiments underway, or at least being planned to even do that, you start to win. Okay, so let's step back. And now, since we can't do this with a gamma ray, let's see if we can do it with photons. And so we have our fluctuating photon, and now we have to do many photons in order to try to make this process work. So we can ask some simple questions. First of all, how far apart can these things be? If they're fluctuating, we can use uncertainty principle to figure out how far away these electrons are going to be. So as an upper limit, we can take as the momentum just mc, and then we can calculate then what the distance would be, and that's basically the Compton wavelength divided by 2 pi. And so that turns out to be about a little bit larger than the nucleus, so that's not so bad. We can ask how long they last. Of course, the theorists will get unhappy with me, but we'll do this anyway. Because time's not an operator, but if we apply the uncertainty principle to time and energy, take the energy to be the energy gap, we can figure out the time. And now this is a zeptosecond, which then validifies my talking in this attosecond seminar series, because this is an incredibly small amount of time. And so that's the time scale over which you have in order to see these electron-positron pairs. All right, so that's not much time, but let's ask the next question. How much work does it take in order to separate these pairs? As I said, they go about Compton's wavelength. So what we need to do is put in enough energy to make them go much further. And so that's a fairly straightforward calculation. So we ask, how much work do we have to do to separate this by the Compton wavelength? Okay, so that's a straightforward. Calculate the work. Then that work gives us an effective electric field, which is about 10 to the 16 volts per centimeter. If you say that you're going to have your laser do this work, you get something on the order of 2 to 4 times 10 to the 29 watts per square centimeter. This is what's known as the Schwinger limit, because this was first calculated for static field. We can't make static fields that high, but we can make laser fields that are starting to approach that, but not quite, because we can't make that. I'll show you here in a second why we can't do that. This is another parameter. We call this the quantum parameter, because if we can have an electric field larger than this critical time, we can then try to separate and make these pairs. Well, our intensity is, record intensity at the moment is about 10 to the 23. So we're 6 orders of magnitude still off. We're getting better and better and better, but we're still pretty far off. And so we're always going to, we're in this regime where chi is much, much less than 1. So there are many lasers coming down the pike now, and here are a few. We have this Corel's, which is the one I just mentioned before. Go back here. The Corel's is the record. So if we go to the lasers, and you can see there's a whole zoo of lasers, And at the moment, Corel and Apollon are the highest energy lasers, and there's another one called ELINP, which is comparable in intensity, but we're still a long way off. There's a new laser being developed here, and this is called the NSF Opal. What I should say is that it's funded to be try to figure out how to plan it, but it hasn't gotten funding yet, at least to build. And that's so if you're interested in this thing, give us some help in trying to build this device. And there's online you can find a way to sign up and sign a letter to send to NSF saying, yes, we should build this. And I think this is quite important. Okay, so now we're at a branch point. I want to look quickly at two regimes. One, a regime where you get this chi that's greater than 1, and the other regime, chi less than 1. And we're going to talk about what we can actually learn in doing that. So for chi less than 1, we're going to be looking at multi-photons, and basically we're going to be looking at photon-photon scattering. And it's scattering which is mediated by the quantum vacuum. And on the other one, we're looking at pair production, and generally what's going to happen is you're going to have many photons. They're going to come in. There's going to be this sort of black box, which means a lot of different things might happen, and then eventually we generate electron-positron pairs. So on the one side, we're just going to be looking at the vacuum. We're not making pairs. On the other side, we're going to be trying to make pairs. And one of the reasons for plasma physicists want to make pairs is because they're interested in making an electron-positron plasma, which is believed to be the source of a lot of some of the strongest energy entities in the universe. So contemporary approaches for the gamma-gamma in the extreme where chi is greater than 1, there are basically 3 different ways to do this. There's laser interaction, so that means we have a laser. We have multi-photon, they're interacting, they're doing things like accelerating electrons. Those electrons then come back and interact with the laser, and then they're making gammas and all sorts of stuff. So it's a complicated process that goes on, but eventually we get E plus E minus. There are ways that you can take a conventional accelerator, like SLAC used to be, or actually still is, in doing some of these kinds of experiments. Or DESI or things like that, where there are some linacs still in existence. And then so you can scatter the electron off the beam. You can make you make gamma rays, and those gamma rays interact with the laser photons to make the cross section a little more attractive. And then there's schemes where you have a plasma. So you have the electron, the laser interacting with the plasma, and a variety of interactions can go through. We have collective effects and things of that sort. All of that leads eventually to what we have. Now, the only experiment that has ever been done that showed positrons coming out was an experiment done back in the late 90s at SLAC, where they did precisely bullet number 2. They scattered photons, laser photons, off the linac, which was running around 50-some GeV in those days, and they were making gamma rays. Those gamma rays then interacted with the laser photon, and then they were able to just barely start to see some electron-positron pairs, because they were basically underneath the threshold. So you're underneath that vacuum breakdown regime. There are several experiments underway or in progress of being planned to repeat this, including another one at SLAC. But there's a Luxi experiment that's being run in Germany. So there are several types of things that can go on. Bullet number 1 is being thought of at Michigan, as well as at the NSF Opal if it gets built, where you're doing photon-photon scattering type of experiments. So let me just say one last thing about this plasma. This is a single beam experiment that's being planned at ELINP, where you have a very complicated process of electrons being accelerated, the beam being reflected off of some type of mirror, then interacting together, and they believe they'll actually be able to see some of these pairs. And so that's pretty interesting. Okay, so now let's look at what we can actually do now, or actually almost now. And so we're going to turn our attention more toward looking at chi less than 1, much, much less than 1. So this also goes back, way back to the 30s, where it was recognized by this guy Halpern that there are two types of experiments. One is the type of experiment that you would have the photons co-propagating and one counter-propagating, all with energies less than the mass of the electron. And so you don't make pairs, but you can actually study the vacuum. So what is it that we're learning when we do that? Well, there's a Lagrangian for the vacuum. And this was developed long ago. The first one was this one by Born and Enfeld, our friend Born. And it was shown here. Here are the properties. It always has two components. One a longitudinal component, which is the L. The other is the transverse component, which is this G. And their Lagrangian, they have the coupling constants have the same value. So beta is some type of there's some type of maximum allowed field. Now Heisenberg and Euler also wrote one down, and theirs is interesting because their longitudinal and transverse components are different. And so you can calculate exactly what those are, and so we've known for a long time what those are. It turns out this lowest order process is the same as the first correction to QED. So everything works out well. The interesting thing here is that there's almost a factor of 2 difference in the longitudinal and transverse components. So that means that if you were able to see this, the vacuum should become birefringent. And there have been lots of searches for that. Okay, so what do I mean by birefringent? Well, okay, so let's go back to our vacuum again. Born and Enfeld have an isotropic vacuum. QED has a birefringent vacuum. So what does that mean? All right, we have our electron-positron pairs coming up, and if somehow they were all lined up in the same direction, then that would mean that if you propagated light polarized in one direction, you would get one speed. If you propagated perpendicular to that, you would get another speed. And so there's been searches looking for just that, the birefringence of the vacuum. And so that one reason is to distinguish these two Lagrangians. The way I like to think about this is just like a normal dielectric. So if you have a dielectric, you put a big electric field on it, then you could polarize the material inside. And so they would all line up. And in that polarization now, you could see a difference in the propagation of the various light. And so here again, sorry, my things are all moving together. They were supposed to be moving at different speeds, but a strong electric field can actually do the same thing. So how do we do that? We basically now would have to have a big field that we're going to propagate in, and then we'll have a probe field to take a look at it. And so here's what we can do, is we take our big pump field, we line up these oscillating pairs, and then we take our probe field, and one parallel and one perpendicular, and I remind you that the parameters are almost a factor of 2 different between these two, and so we should see a difference if we measure this. So we either can look at birefringence or we can look at the direct signal. Now this has been gone on for a long time, and I'll just rifle through. Nobody has been able to get sensitivity low enough in order to see this. This is a photon-photon scattering measurement. It's a very long-term experiment using very strong magnetic fields. You get the same answer. They too come up a little bit short. This is being recast with X-rays because the cross-section is higher. And so there's a chance if you do this experiment with X-rays, you might actually be able to see something. So that's going on as well. Now, the simplest possible experiment you can think of is a direct photon-photon scattering experiment, which we wrote a paper on a few years ago. So you have a big beam that comes in, we have a probe beam that comes right back on it. which is a little bit challenging, but we have some ideas on how to do that. And you look for scattered light. Now, if your probe beam is known very well, then you know the properties of its scattering properties. You know how it diverges. And then you can look for deviations from that divergence just outside of this mirror. Turns out you can do that. It's a very hard experiment. May not be the best way to do it, but it is doable. But you need intensities about an order of magnitude or two higher than what we currently have. But that's one way to do this. But this is not the only way in which to try to do this. And I'll tell you in another one in a second. But I do want to point out there's another reason for doing these experiments, not only just to look at the parameters, to measure those parameters, which needs to be done because these things have been known for almost 100 years. So we need to measure these things. QED has never been tested at this level, and so that needs to be done. But at the same time, there's a problem with the standard model. It doesn't predict several things, like why there's a discrepancy in the number of particles and antiparticles in the universe. And so, I mean, that's only one thing. We don't know what dark matter is. There's some ideas of these things called axion-like particles could be part of that dark matter. And there's a cross-section for these things. And if they exist in the range of our laser energy, they would deviate the parameters for QED in a direction that can actually be measured. And here is, most of the experiments are based on astrophysics and astronomy, and there have been very, very few laboratory experiments, which really needs to be done. And so these things are quite important. And this is again, the Lagrangian. So, but I told you the photon-photon scattering is one way to do it. Another photon-photon scattering using X-rays here with a dark spot, so you can actually see the light is another possible way to do this. Another way is a four-wave mixing, and this has a lot of merit because the four-wave mixing experiment means you're looking for a signal that's very different from the two beams. The downside is you got three lasers that all have to line up together. Okay, so let's look at a typical multi-petawatt laser. Typically you have two arms because you want to have one beam to be the pump beam, one beam to be the probe beam, and it's a whole series of things. As I mentioned, the beams have to get quite large in order to get these to go. The laser that's being designed at Rochester in the NSF Opal will have two 25 petawatt beams, and so that will get us much closer to where we need to be in order to do that. Now, it turns out we have no way in which to measure the intensity directly. We don't know how to do that. We can only estimate it. We can measure it at low power and then turn up the power and hope and pray that the beam behaves normally, but we don't know how to do that yet. So there needs to be a direct way to make measurements. As I mentioned, we currently can't do that. We have to infer things. We've developed a couple of techniques that could be useful. I won't go into the details of those. Here, I'll give you some references. You can read about that. I'll tell you a little bit about how we do this in a second. We actually don't even understand how ionization works. Now, ionization turns out to be important because the two techniques that we have developed look at electrons born in the focus. And unless we know how the electrons come out of the atom, we don't know how to do that. Ionization at the lower intensities are basically, we understand how that works. The lasers can be treated classically. The ionization then can be treated quantum mechanically, and we know basically how to do that up to about 10 to the 18, 10 to the 20 maybe, but higher than that we don't know yet. Beams have aberrations. How do we assess those aberrations? And then of course, as I mentioned earlier, we need to have a pure vacuum. All three of these things we are currently working on. I don't know why those weren't supposed to be there. So why am I going through this twice? I'm so sorry. The electron ejection. Here we we put a little bit of gas in the focus, and we ionize that gas, and it's going to produce electrons. And those electrons will get accelerated. We're going to measure that acceleration. And here, to measure that acceleration, we can look at the electric field. The electric field now tells us how much the electrons are going to be accelerated in the direction of the electric field, which is perpendicular to the propagation primarily. The K vector tells you how much is being pushed forward, and that comes primarily from the magnetic field. And so that combination now gives us an angle, and then we can actually determine the angle of ejection of the electron is a ratio between these two momenta, and that tells us something about how much energy it has. And then we need to couple that back to the A naught, which can be done in a Gaussian field, which is which we have done a lot of. And then we have this a nice curve that we can get. And we've done a lot in this regime. It turns out, though, the focused laser does not look like a Gaussian beam because it's a flat top focused to a spot, and we can see that in the upper trace here, there's some dark spots along the beam propagation, which is to the right. And those dark spots, they're called lamelle minima. They can scatter the beam. And so we're in the process of trying to simulate how these electrons come off. Not only that, if we actually look at the focus field, it's a vector field, and the vector field is quite curious. And this is what it looks like near the focus. We have these zeros in there, or minima, and then the beam breaks up. And so it's a quite complicated field. And so we have to determine what we expect that the electrons to look like when they come off of that, and then compare that to what we actually measure. And that we're in the process of doing that. Another problem here are aberrations. This is a nearly aberration-free beam. And so the left image is the spot measured at very low powers, and we just put in a microscope objective and we just measure the intensity. And so we can then, from that measured intensity, we can scale that up to the higher intensity, and we estimate what we expect the peak intensity looks like. The right image is an image taken from the electrons that I mentioned just in the last slide, and we see it's a nice uniform distribution. And this is a real measurement, not a simulation. Usually, however, the beam looks more like it does on the at the top. The spot and the focal spot and low power looks a little bit strange, and then the electrons that come off are also aberrated, and so that's a big problem. But we've investigated this, and we've seen that we can associate some of these aberrations to well-known things like coma and astigmatism. And so now we're thinking of how we can now use machine learning, the AI, to go backwards to take these images as we see on the right, and then change that so that we get images that are more consistent. And so that's we're in the process of doing that. The last thing we are also in the process of doing is generating a pure vacuum. And now we can use, again, the electrons can scatter. So we won't put electrons in. We get electrons basically from the background gas. And primarily, even at high vacuum, you always have hydrogen. So there are always electrons coming around and always protons. Turns out that if we have a pre-pulse that comes in, that pre-pulse can scatter the electrons. And the picture on the right, the lower picture on the right, shows that we actually saw that. So we put in a precursor pulse, it scattered the electrons, we follow it by a larger pulse, and we can see that fewer electrons are there. And so this has a possibility of actually working to clear the vacuum. So the three things, we're actually making some good progress on that. Well, I'm coming to the end here, so let me conclude here. So I hope I've shown you a little bit about QED and what we can learn through photon-photon scattering, and also what you can learn if you have enough intensity to create pairs. There are several facilities now either underway. I only showed you a few that are actually should be coming online soon. There are other ones which even higher intensity can be reached, which are quite exciting. So the techniques that we're looking at are really important because we need good diagnostics. And so we're working on ways in which to perform this diagnostics. We have shown that this, looking at the electron acceleration is viable. We've shown that the ponderomotive scattering is viable, but there's still some open questions. And how does ionization work properly at these higher intensities? We don't know how that works yet. We're thinking about some of those. And then we need to implement these good ways in which to clear the beam. So this work that I talked about is a collaboration, and there are three primary places where we collaborate. We have a colleague in Canada, we have colleagues in Europe, colleagues in Rochester, and then us, and then we have some people at Stanford who sometimes interact with us as well. And here's sort of a picture of a variety of teams doing various experiments. So I want to end with an advertisement of an ebook that I wrote, and I'm not gonna show this, but if you'll be able to pick out the URL here. This is basically talking about the quantum vacuum, and it's talking about at a level that is without any mathematics, basically, and it's at a level that I hope you would be able to understand. And so let me stop with that, and I'll take questions.
So thank you so much for this talk. It was really, really interesting. Other questions, comments? Just raise your hand or write in the Q&A tab. And the people on YouTube, just write on the live chat. If you're a subscriber, you can also ask questions. And I can see we have quite a lot of people on YouTube right now. So hang on. Sorry?
Oh, I don't see that here. Huh.
No.
Well,
No, there is no, I mean, I can ask one, and it's out of curiosity for someone who is a theorist. You mentioned that people saw positrons in 1999 at SLAC, and then now they're trying to see again why this hiatus for so many years.
these are very hard experiments.
Mhm.
There are lots of things you have to worry about. The original experiment at SLAC was done with a very low power laser. I think it was like 10 terawatts. And the people who did it spent a lot of time. I mean, they weren't sure it was actually going to work. They had to have the beam time to do that. And so getting beam time was important. Now, in those days, SLAC was running, SLAC was almost, it's 2 meters or so, and 2 kilometers or so, or 2 or 3 kilometers, something like that. And it's made in 3 different sections, and they were all working together. Now SLAC has been divided up into 3 different sections. So the highest intensity, I think, is on the order of 10 or maybe 15 GeV. So it's harder to do the experiment now, but we have better lasers. The long hiatus is just because it was such a hard experiment. I think everybody was exhausted. But everybody recognizes you need to do it again. Unfortunately, at SLAC, there's no petawatt laser. If they had a petawatt laser, this experiment would be a lot easier. And so it was a matter of laser technology as well. There are higher energy lasers elsewhere, and so a lot of what people are trying to do now is using the laser to accelerate the electrons and produce the photons at the same time. There are caveats with that because the laser beams jitter a lot, and so keeping 2 beams at the same place at the same time is hard. And so they're just hard experiments.
Mm-hmm. Okay. Yeah, it was a long time, right? Yeah, long ago, but it is interesting to know that it is so hard. Come on, those watching, don't you have any questions? Just use the opportunity. Raise your hand if you want to talk. People are quiet today. Sometimes it happens, they need to be animated, but I think it's my
Yeah.
job to grill people as well as a chair. So, yeah, I mean, it's just amazing what can be done with the vacuum. And you said something that kind of surprised me. You said that you don't understand ionization very well in this regime. Can you elaborate on that?
Well, we have never tested it.
Okay.
So here's the issue. When you're looking at valence level electrons, we have a really pretty good idea what happens. For example, you have barrier suppression ionization. And so, the electron comes out and it comes back and it can rescatter. A lot of that has been done. There has been a lot of calculations on tunneling and how that takes place. You can basically ignore the magnetic field, so all the dynamics is driven by the electric field, because the speed of the electrons as they come out, well, the speed at ionization is basically non-relativistic, and so only electric field matters. Now, as you go deeper and deeper into the core, now the electron speeds can be higher. My theorist friends always keep telling me it's still, when it ionizes, it's still going to be non-relativistic, which makes sense because, of course, it's if they're just barely over the barrier, it's going to be they're moving quite slowly. But tunneling, we don't know how that's going to work, and there's some models, and we're looking into that right now. They've never been tested, and so we are running the first experiment to try to test that in a few weeks, actually, in France, on the Apollon laser, which should get us 10 to the 22 watts per square centimeter. So we'll be able to run our first test, and that's where it will be critical. So it just has never been tested, and we don't know what happens. If you get these big systems like xenon, then you have to worry about which electron comes off first, which shell is coming off, and that's a little bit challenging. We just don't know how that works, and so we're looking into it.
Okay, so we have a question now from our audience, from an anonymous attendee. It's a very interesting topic and nice talk. What problems can be solved by conducting the study on quantum vacuum?
What problems can we solve? Well, the first is what we're trying to do is the QED is the most tested theory we have. However, it's only been tested at low light intensities. It tells us what's going on in big scattering experiments where, of course, the energy is quite high. But from the photon side, it's very low. So the problems that we're looking at, and there's no guarantee that this is going to be solved, but the problems that we're looking at are, where does dark matter come from? We have no idea where dark matter comes from. There are theories which suggest that axion-like particles may be those dark matter particles. Axion-like particles have a mass range of almost 20 orders of magnitude, so nobody really knows what they are, and so doing experiments are important so we can put some limits on where things are. Astrophysics type experiments have put very large limits, but those type of experiments have very large error bars at the same time. So laboratory experiments are really important. So that's one thing that we need to do to find out, does QED tell us the right answer when we go into the nonlinear regime? Because again, it's been highly tested. Of course, these high energy lasers are useful in medicine for accelerating electrons right now, and then maybe positrons. We know that positron therapy is different than electron therapy. Hadron therapy is also different, and so there's some medical possibilities. As I mentioned, when we get to 10 to the 24 or 10 to the 25, we can accelerate protons in the same way, and you can imagine we might be able to accelerate light atoms like carbon. ions or alpha particles, something like that. So there may be some applications there in medicine. These experiments lasers are, they call them tabletop, but you have to have a pretty big table, but they're nowhere the size of an accelerator. So they're cheaper than an accelerator, they're more compact, and so one might be able to have these in a variety of places as well. So there's scientific questions to address. The technical questions, of course, we don't know yet, but you could have asked the same question when the laser was invented. What was it invented to do? And now you can't live without a laser. So I have no doubt that once we start to understand these things, what we can use them for will start to scale.
Thank you. That is very interesting. And we have one question from YouTube as well, from one of our subscribers. It is a relatively new topic for me. So the question, can you please explain the difference between quantum vacuum and classical vacuum again? Quantum vacuum, is it the ground state of, say, an atom? Can you associate with that?
Well, okay. So no, the quantum vacuum really has no particles in it. So there are no electrons. It's hard to get rid of the photons, but because of this vacuum polarization, and because the electrons and positrons can come into and out of existence on their own, there are going to be photons associated with them. Some of them will be virtual as well. So the quantum vacuum is devoid of matter, just like the classical vacuum. And when I say matter, I say real matter. But we could have fluctuating matter that's virtual, that comes into existence from time to time. So all of this is there. There's some theories which talk about the speed of light and how fast the speed of light is because of the density of these fluctuating particles. And so, on a quantum level, the vacuum all it has is fluctuating particles in it. The classical vacuum has nothing in it. There's nothing. The quantum vacuum, there are no energy sources. That is, there's nothing that can generate energy, but there are these fluctuations that come in and out of existence constantly. And the same thing happens when you go to higher, more massive particles. The lightest particles we know of are electrons and positrons. Some of these axions would be lighter particles, but they don't seem to couple very strongly to photons, and so we don't see them on a regular basis. And this is why, again, we need such high intensities. If they couple at all, if some of these theories which tell us how they couple to the electromagnetic spectrum, that's where it's going to be found.
Okay, are there further questions? Comments? Would anybody like to raise their hands? Maybe to have a chat with our speaker? We have something else. It's coming. They're coming. Felipe Zapata, thanks a lot for the great talk. I have a question concerning theory capable to describe ionization in atoms at the relativistic level. Do we need to use QFT? This is using the Dirac field, or is it possible to use quantum Dirac theory?
There have been some papers with the Dirac theory, but as I mentioned, most theorists believe that because the electron escapes from the atomic potential non-relativistically, that the Dirac approach is not warranted, and then Schrödinger tells us what we need to know. That's true until the electron leaves. Once the electron leaves and it's in the field, now everything changes. And so what one doesn't know is that how the electron then is going to be detected. So when we detect the electron, how do we disentangle how it came out of the atom from what we actually detect when it is out of the atom? There's another issue which I didn't mention at all, and that is when you're looking at ionization, your normal atoms like oxygen and nitrogen and things in the air, hydrogen, all ionize at such a low intensity, they never see the most intense part of the beam. It's only when you get to really heavy systems like xenon. The xenon is predicted to ionize the last K shell at 10 to the 25 watts per square centimeter, something like that. Now, when those electrons are born, then they come out and they see an enormous acceleration. And as you know, a charged particle accelerates, it's going to radiate. And so that radiation is going to be on par with the energy that it gains. And then so there's something called radiation reaction that may take place. This is probably not going to be important at 10 to the 23 or maybe not even 10 to the 24, but at 10 to the 25, it's probably going to be an issue that one has to worry about. And so it's really getting at these really high levels that we don't know how, what we detect and what was true when the electron was actually born. We have to disentangle that. And so that's a real problem that we're going. I don't foresee a problem where we are now, so the experiment that we do at 10 to the 22 probably will give an answer that we recognize. But going forward, where the lasers are headed is what we're trying to study. But nobody's ever done any measurement of ionization where at 10 to the 22 yet. I mean, the highest is around 10 to the 20, maybe 10 to the 21. We see ionization up there, but nobody's studied it to know whether or not we can predict it properly.
Is that okay with you? Would you like to pursue further or talk to our speaker? If so, you are welcome to talk. We have allowed you to talk. Sounds creepy when you say it on Zoom, but we did, so you can chat if you want. Hello?
Hello, can you hear me?
Absolutely. Yes, we can.
Okay, okay. Sorry, it was on mute. Thank you so much. It was a incredible talk. Thank you so much. And bueno, I really like your answer. And also, I have another question. So, also because I'm a theorist, so concerning the do we need to reinterpret the? So, what do we do from a theoretical point of view with the negative energy states, the solution from the Dirac equation? For example, if I want to simulate this kind of ionization from a xenon atom from the core levels, it is possible to include them in the simulation and to describe this virtual pair creation? Or have you thought about this question before? I don't know, or some of your colleagues, because I'm kind of also interested in this kind of questions. And well, thank you.
That's a good question. I'm not a theorist, so I don't know that I can give you an answer that you'd be satisfied with. Again, my understanding is the problem will occur when the electron becomes free. Now, I have seen some ionization discussion using the Dirac equation. Of course, that's a lot harder than using Schrodinger. Whether there's anything new that comes out of that, I cannot tell you. That would be very interesting from a theory point of view to discover. Or actually, probably more importantly, under what conditions would one absolutely need to have the Dirac equation? So obviously it's got to be relativistic. And are there going to be some spin issues that come to play? One of the problems as for xenon, barring the fact that it's got so many isotopes, that's another issue. But it says because you got these, it's the P shell. The K shell is probably okay. It's the P shell that's going to give you problems because The different angular momenta states, we don't know how to couple those together. And whether Dirac will tell us something about that or not, I don't know. Whether there's any fluctuation on that level, because the ionization starts to occur quicker, I didn't show pictures about this. Ionization is really occurring on an attosecond timescale. So ionization happens very rapidly at these intensities. It's not, it's in a fraction of a cycle. So the question is, what all can happen on that timescale? It's not quite the timescale of fluctuations, however. I mean, that's really another 4 orders of magnitude, or actually more or less. So I'm not sure that we're getting down to that level yet. That we'd have to have shorter pulses to see that. Maybe if we're looking at ionization at high frequency, maybe that becomes relevant, because then the length of the single cycle is much faster. But that's a good question. I don't have the answer to that question, but I find it is interesting. So I guess what I would suggest is looking at high frequency first, because that's where the ionization would occur more rapidly, even though we don't know how to make these devices yet. If you look at the high frequency ionization, the petawatt equivalent at high frequency, maybe that Dirac would be important, because now the timescales get much shorter. But as I mentioned, if you accept the fact that the timescale is on the order of half a zeptosecond, then that's sort of the level you probably have to worry about.
No, super interesting. Thank you so much. Thank you so much.
So, are there further questions, comments? Do feel free to ask. Also, for those on YouTube watching, I'm glad to see that there were some people also in there. If not, we're going to end the streaming. You can still talk to our speaker in a more private setting if you don't want to be everywhere on the internet. So for those watching us, thank you so much. For those on YouTube. And thank you also to Professor Hill for joining us today and for giving us the opportunity to hear about his work. And
thank you so much for the invitation. This was fun. I think my colleagues here, David in particular, and Eric, they were very, very, very helpful to set this up, because this is much more fun than sitting at my desk looking at a screen. So they set this all up for me. So I thank them as well.
Absolutely. We thank everyone who is watching us, and hope to see you in 2 weeks.